So question in nutshell is you are given an undirected graph containing n nodes. Right now, I'll just say to you, don't worry about the term graph. It is not a graph problem. The way we will see, the way we will solve, we don't need graph. Whatever you have learned so far should be good enough for you to understand this. So idea is this, you have few numbers, let's say 1 to n. That is a guarantee that you will have numbers in a fixed range 1 to n or 0 to n, but I'm taking 1 to n. You are given two types of operations to perform on the numbers, and those two types of operations are union. So initially, if I just take n as, let's say 8, so you will have 8 numbers, 3, 4, 5, 6, 7, 8. You will be given an operation union. Union is in a sense saying that you are joining two numbers. So union of A comma B. So treat it like union or join. So if I just say to you, join 6 and 8, it is like initially they were independent nodes, and now you are joining 6 and 8. So you are kind of making a group of them. So it is like 6 got connected to 8. Then if I give you a next query as that join 7 to 8, so you are joining 7 and 8. So now the structure will be your 1, 2, 3, 4, 5 are separate, and 6, 8, 7 are joined together. So this is the union operation that combine things together. After that, there is another operation called find. If we give you again A and B, you just have to tell they are connected directly or indirectly or not. So if I ask you, find of 6 and 7, are 6 and 7 connected? Are they reachable from each other?
Yes.
Yes, they are reachable. So union is join them, and find is just tell they are connected or not connected. That is the question about. So now if we come back, so it is saying we are given an undirected graph containing n nodes. There are no edges initially. That means initial state is also told to us. They were totally disjoint. They were separate groups. And you will be given few queries of the following format. First query you can call as a union query, which adds an edge between U and V. Second query is like find query, where you have to tell whether they are connected or not connected, whether there is a path. It can be direct edge or it can be a longer path. So this is what is given. Now, if you come here, see, n can be 10 to the power 5. That means we have 10 to the power 5 separate nodes. And we are given 2 into 10 to the power 5 queries, which is huge. So for each query, you have to give, for join query, you have to combine them together. And for find query, like this is union query, this is find query. For find query, we have to print answer just yes or no. So if we try to interpret this input, what is the meaning of first line?
Join 1 and 2.
Join 1 and 2, because it is first type of queries add edge. In fact, if we see before this line, there is 3 and 4. First line contains n and q. So 3 is n. That means there are 3 vertices, 1, 2, and 3 to begin with. And there are 4 queries that we need to process. First query is join 1 and 2. So we have joined. Okay. After joining, what is this query asking?
Find if 1 and 3 are connected.
So what do you say? 1 and 3 are connected or not connected?
No.
At this moment, no. So we, for every query of type 2, we have to print yes or no. So no is printed for this. Now next query is
Join 2 and 3.
join 2 and 3. And
Correct.
after that,
Yes.
answer is like, are 1, 3 connected? Answer to that is yes. So question wise, we are clear?
Yes.
Great. So now this is the question. And what we want to establish is we will work out certain things so that we grasp the concept well, and then we will eventually come to the original problem. So for now, what I'm doing is I'm putting some intermediate state where we have processed some union queries and we have formed some sort of, let's say, structure Okay, so this is kind of after performing some unions, we have landed up in this state. Now I want you to visualize these each of these things as a tree. And can you tell me what is n here? Number of nodes here in this case? N is 9. Yes. Now if I ask you for 9, node number 9, what is relation between 8 and 9? If you see this as a tree, what is the relation? In
8 is
tree,
parent and 9 is child.
8 is parent and 9 is child. Yes, so it's a parent-child relationship. Same way, if I ask you, 4 is a parent of 6, 3 is a parent of 5, 3 is a parent of 4 as well, 1 is a parent of 2. So I have just tried to make it a parent-child relationship. Why we are doing parent-child relationship is there is a group, and in each group, we want to designate root as identifier of that group. So root is an identifier. If we want to know 6 and 5 are connected or not, what we would do is for 6 and 5, for both of them, we would ask who is the root of 5, who is the root of 6. If two nodes have same node as root, what is the meaning of that?
They are connected.
They're connected. Okay, so we will use this notation of root to answer our find queries. So there is a notion of root that we will take. And now this root thing is something that is easy to represent using just an array. So I want you guys to write, if you have pen and paper, write on that. If you don't have, just get a pen and paper. But I want you to take an array, ignore 0th index because we don't have 0th node. But I want you to, for this tree that I have given you on the left side, take an array of size 10. And for each node, I just want you to fill at each index, I just want you to fill its root node. And just type done once you are done filling this array. Treat this as a root array. And when you are filling, if you get any doubt, any confusion on what we should fill in any cell, just let me know. Okay, all done. Okay, who
So,
did you fill? Yeah,
sir, for 1, 3, and 7, the root will be 1, 3, and 7 only, right?
yes. For that's a good question. So for one itself will be the root. So what will we fill in 1?
1,
1. For 2,
1,
1. For 3,
3,
okay. For 4,
3,
for 5,
3,
for 6,
3,
for 7.
7, 7, and 7.
Okay. So if you have this root array available with you, can you find root for any node? Yes. If you can find root for any node, can you just tell that two nodes are connected or not? So our find query gets answered easily if we have root array. Okay. Now I want you to think of one more array rather than root array. I want you to build similar way. I want you to build parent array also for each node. Again, 0 index empty. 1, 2, 3, 4, 5, 6, 7, 8, 9. This time you will not fill root. This time you will fill just the parent. So who is the parent of 1?
Should be null.
Itself.
It should be null, but we will use same concept that we used in root. If
Okay.
this is the root, then we will say he's his own parent. 1. For 2,
1,
for 3,
3.
3,
for 4,
3,
3.
5,
3,
6,
4,
7,
7, 7,
8.
8.
Okay. Now, if you see, we have moved away from root array to parent array, because from parent array also we can find the answer. If I just ask you, if I give you parent array and I say find root of any node A using just parent array, imagine your parent array is globally available. You don't have root array, but you have parent array. Just think for a while and see, can you write find root function easily for any given node? That means if I give 6, I want its root to be 3, and you have to manage to find that using parent array. Yeah, just let me know if you are able to visualize. Like once you come to a point, you say, yeah, I can write this function. This is not a big deal. Okay. Ruchika
Yeah,
says
sir.
yes.
Easy.
It's easy. Yeah. Okay. Ruchika, Suhas, Kishore says easy. Vishwa, what about you? Joshua, you're there? Or Joshua slept? Okay. Unable to understand. Okay. So out of other 3 who said it is easy, how many of you have a recursive solution? Okay. No one? Okay. How many have
I
it?
can write, sir. Yeah, I can write. Takes few seconds. I can write.
Okay. How many have iterative solution? All 3 of have. Okay. Kishore says he'll write iterative. Ruchika, what is your solution? Yeah, Ruchika. Iterative, recursive. Okay, I think Ruchika got disconnected. Anyway, she will come back. So, can we say if A is equal to parent of A? See, if any node, for example, 1 is its own parent. If A is equal to parent of A, what does it mean, Joshua? Yeah, Joshua, any member is his own parent. It's a root. Joshua, is that clear? Okay, return A. But if it is not its parent, then, for example, 9 is not his own parent. 9's parent is 8. So what we should do? We should also find 8's parent. 8's parent is 7. We go to 7. 7's parent is 7 himself. So can we, in such case, can we simply say we should return find root of parent of A? Parent of A. Whatever answer that gives, that is the final answer. Yeah. So Joshua, recursive solution is clear. Yeah. Can you write iterative solution also similar to this? Just a while loop. Yeah. Now others said that they have iterative solution. Ruchika, what was your solution? Iterative or recursive?
So recursive.
Okay. So recursive, but now we have recursive in front of you. You can write iterative solutions also easily for this.
Yes. Yes. Sir.
Okay, great. Okay. So find root is a function that essentially we need. If you have parent array, using find root, you can answer join query. Oh, sorry, you can answer find query. So In union find, we had a find query bool. Let's say find root function is there and you have parent array only. Then what will find function look like? You have to tell whether A and B are connected. Because what will be find function looking like? What will you do to tell A and B are connected or not? For example, 6 and 5 are connected or not? You have to tell.
Return find root of A is equal to find root of B.
Absolutely. So return, basically call find root on A and find root on B. If they both are giving same root, then they are connected for sure. One liner code done. Find root is enabling us. FR is just find root. Okay, so we have solved half the problem of answering query of type find. Now we just have to worry about how to create this structure and how do we define union function. Once we have that, this problem will be more or less under control. Okay, so in order to do that, I'll have to take some union operations also. So let's say when initially we had 1 to 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Initially you had this. Can you tell me what parent array will look like at this moment? Initially when none of them are connected, what will parent array look like?
1 to 9.
1 to 9. So each element will be its own parent.
Yes.
That is why this data structure is called disjoint sets. So right now we are saying every node is a disjoint set, is independent right now. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if we are doing union of 1, 2, when you have this operation, we will use a strategy. What we will do is currently, I'm using a shortcut right now, but currently we will say first guy we will make a parent and second guy we will make a child. Is this making sense? First guy will become the parent, second will become the child whenever we do a union operation. So in this union, if we call a function union of 1, 2, what modification you will do to the array?
2 will have 1.
Yeah, so if we are talking about there is a union function, union int A, comma int B, and you have to update parent array only. So what will be the line of code that you will be writing to a union?
Parent of B is equal to A.
Parent of B is equal to A. All of us are in sync with this. Okay, so we are essentially going and saying parent of 2 is 1. So that means we are updating 2 to 1, and pictorially, this is what it becomes. 1 is gone. So now one disjoint set has reduced. We are left with 8 sets. Okay, so you see that we are gradually bringing it in this shape. Union operations will bring it to that shape. Now, if I say do a union of 4 and 6, so what will happen? Same one line code will work. So
Here, do we need to add the condition if both are disjoint, then only?
yeah, we can do that. That's a good point. But currently, will that make any difference?
Currently, no.
Currently, no. Yeah. So gradually we will come there. Yes, we will put that check also. So currently, no. So 1 became parent of 2. Now, can we say 4 becomes parent of 6? So 6 gets modified. 4 becomes parent of 6. And one more set actually reduces from here. So we land up to this state. Okay. Now, if I say connect 3 and 5, union of 3, 5. So same thing. We will go to 5 and modify its parent to 3 now. And 3 becomes parent of 5. And also keep in mind that we want, whenever we join two things together, we want both of them to have only one root, because the root is actually representing that set. Okay, so at this moment, we have got situation 3, 5 is connected. Now, if we join, let's say now if we have to do union of 5 and 6. So what should we do when we are doing union of 5, 6? Who should become the parent? Who should become the child?
Actually, 5 should be parent, 6 should be child.
Then who will be the root?
Yeah.
If you see 5 is connected to 3 already, 6 is connected to 4 already. If we are joining 5 and 6, and if we join them like this parent child, then do we really get a root?
No.
No.
Then
So,
we can
but
make 5's parent as parent 2, 6 also.
absolutely. So basically, we don't write union operation like this. What we do, let's find the root of B. Let's find the root of A. Why not join them as a parent child? Is it making sense? So root of 5 is 3. Root of 6 is 4. So let's do, earlier we were doing this will be parent, this will be child, but now we are saying root of this will be parent and root of this will be child. So 3 becomes parent of 4. So we are doing that relationship between roots, not between the A and B directly. So this line will change to parent of
Root,
find
find,
root of B
find root of B.
becomes equal to find root of
Find root of A.
A. That's it. That is one slight change we are doing. That is where I was saying earlier, I'm taking a shortcut, but this is how we will do so that we can have one identifiable root. Okay. So yes, that is disjoint set, union find disjoint set. So if I ask you now, union find disjoint set data structure is just a parent array of size n. First of all, you set up. So setup is like initialize it. So how do we initialize parent array initially when they are disjoint? What was the logic?
Just each index has its own value.
Each index has its own values. Can I say for int I is equal to 1, I less than equal to n, I plus plus, we can just say parent array of I is equal to I. Initially, that is the situation. Okay. Then we say find root. This function earlier we had written as recursive. Can you quickly implement the iterative version and just tell me so that we fill it? Find A and B. We'll be simply using find root. Find root of A double equals to find root of B. And there is a union function. Parent of, now Ruchika was saying something here. Ruchika, we will incorporate that now. First we find root of A, and then we find root of B. And Ruchika was mentioning that if their root is already same, then why should we do it again? So we can say if RA is not equal to RB, this is just to avoid duplicate queries. In that case, what do we do? Parent of RB is equal to RA. That is what we talked about. So ideally, if you see main work is done by find root. Yeah. Can you write that function quickly? Iterative version of that. Recursive we talked about. Just write iterative.
While parent of A not equal to A equals
Okay.
parent of A.
They are saying while parent of A not equals to
A equals parent of
A equals parent of A. That's right. So you are moving up
return A.
and in the end return A. Yep, that's the code. Because if parent of A is equal to A, then we are directly returning A. Otherwise, we are just moving up the ladder. Now, it is just an array problem. Visualization was nice that it gave us some concept. It's an array problem, right? Okay. Now, one last thing, a small tweak that we have to do here is this. Imagine somehow our unions landed up, there are 10 to the power 5 uh, nodes in the real problem with which we started. There are 10 to the power 5 nodes. What if it becomes like this? Your tree is becoming something like this, and all 10 to the power 5 are arranged like this, let's say. Now, if I every time I ask find between this and this, and let's say this tree is very longer, will my find operation be big of 1? Will find be, or will find root be big of 1? Find root be big of 1 if the depth of tree is very high. Okay, yes or no? What do you say?
Big of 1.
Big of 1. Will it be fast? Or we will have to go up here, up here, up here. Every time I'm asking this node and this node are connected, U and V. Is find root or find function really big of 1?
No.
It is not. But find queries are mixed. If imagine with 10 to the power 5 nodes, if it becomes like, let's say 10 to the power 4 path is just like a flat hierarchy, and rest all nodes are just children of that. That means every find operation will take 10 to the power 5, 10 to the power 4 iterations. Because from here you have to traverse entire line. So there is a list here and all of them are children. So it is inefficient right now. So we do some more trick in this data structure that makes even find root efficiently. So what we do, let's say for this U, we are asking find root. So find root asks, who is the parent of U? This. Who is the parent of this? Who is the parent of this? Who is the parent of this? Ultimately, we return that answer that is the answer, that is the answer, that is the answer, that is the answer. When we do that, so we flatten the tree. What we do, whatever answer is being returned, we start flattening the tree. For example, let's say this is U, V, W, X, Y. Our find root function that we are writing, U is asking V, V is asking W, W is asking X, X is asking Y. Now, whatever value Y is returning, what if we update parent array with that answer? So if parent array, parent of X becomes Y, there is no change here. But whatever answer is returned, parent of W, if I say set parent of W to Y, what change will happen in this tree? If I set parent of W to Y, what change will happen? It's like W will start reporting directly to Y. Same way, if we say parent of V is also Y, so we will also start directly reporting here. Parent of U is also Y. It will start reporting here. So basically, as we move up, I'll just show you that in the recursive code. Our recursive code was if A is equal to parent of A, we were saying return A. Otherwise, we were saying return find root of A. That is what find root of parent of A. That is what we talked about find root function. Now we are saying whatever answer is being returned by the parent, why not we do this? Parent of A is equal to this. It is like flatten the tree. And same value we are returning again. So if Y was returned, parent of X became Y. Now same Y is being returned to W, parent of W also becomes Y. Same Y is being returned to V because that's the root. Parent of V also becomes Y. Same value is being returned to U, parent of U also becomes Y. So every time before returning the value, similar to dynamic programming, You are just remembering and updating the answer. So this will flatten the tree, which will make next time find root will be fast. And the moment tree becomes flat, everyone is starting to connect it to root. How much time will find root take?
Of 1.
Big of 1. Okay. Now this is easy to do here. I'll leave this as an exercise, like how will you do it in iterative code? How will you update the parent in iterative code? So if you see this technique in union find is called path compression. So this is path compression. So that's it. This is the concept. Now it will enable you to solve this problem, whether two nodes are connected or not connected.
This is medium difficulty.
Yeah, this is medium difficulty because people who know the concept of union find can do it. Like this is getting started problem of union find.
Okay.
Yeah, so ideally it is like once you know the concept, it is easy. So union find. This is the article, and in fact, the reason I'm taking it here is there are some questions that will be given below. So code forces, Podge, hacker earth, okay, top edge, I don't know. Yeah. And in fact, you will find a lot of questions on this in code chef, code forces, hacker rank on union find. In competitive programming, yeah, this concept is considered to be like you should know union find to solve such problems faster. And yeah, there is one more concept which I have skipped, which is union by rank. So it is basically when you are merging two trees, who should become the parent? There is some concept behind that also, but that is not needed right now. Okay. So ideally, what people do, there is people make a library out of it, and then they use that library when they are participating in the contest. Union find disjoint set. In fact, I'll put all this discussion in the notes, but if you see here, we have implemented these functions in C language, in C++, Java, and then there are many questions related to this. So I can put this in today's class notes. So at least for you guys, it will make sense, whatever we have discussed. Yeah, so I'm putting link here. That is one problem link also. This is the problem link. I'm putting that also here. Last thing is whatever notes I was typing, let me write that also here. And this discussion, though, I think video will carry. I'll share this recording with everyone in our group.